Welcome everybody back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. Before we move on to today's class, let's do a brief recap of what we had covered the last time around. So last time around, we looked at the basic structure and function of biological neurons. We saw how dendrites receive the signal which goes into the soma or the cell body of the neuron, which integrates them. And once a threshold is reached in the membrane potential, there is a signal which flows through, or the action potential which flows through the axon. And the axon is what transmits the signal. And through the synapses, this signal is sent to the next set of neurons. Okay. Most importantly, the biological neurons do not work through continuous voltage levels, but through discrete spikes or action potentials. We also discussed how neuron firing is an integrate and fire process. Thousands of excitatory and inhibitory inputs arrive at the cell body, and as we described, the membrane potential integrates all these, and if a threshold is reached, then only there is a firing. Another very important thing that we saw was that each neuron is connected to 1,000 or even 10,000 other neurons. And this is what gives the brain this massive parallelism and large fan out. And that is why simulating all details of the brain is very, very difficult. We gave the example of the IBM Blue project, which consumes a megawatt of power to simulate just 1% of the brain's operation. So neuromorphic computing does not try to replicate every biological detail, but aims to mimic the essential features like spike-based communication, local learning, and event-driven computation. What makes brain really special and low power. Finally, we also looked at the leaky integrate and fire neuron model that you see on the slide over here. And this captures the behavior of the neurons in electrical engineering terms, because that's the final goal, to be able to make devices and circuits which can mimic this biological computation. However, we saw that the leaky integrate fire neuron, which was built using an RC circuit and a threshold comparator, although is able to mimic all the functions of integration, leakage, and firing, it comes at a large cost of both power and area scalability. And therefore, we want to look in today's class of how do we build neurons that can mimic all this function just with a single nanoscale device. Okay. And that is the focus of our class today. But before that, remember our homework problem. It was to write down the circuit equations for this above leaky integrate and fire neuron. So let us look at that first. So as you can see in the membrane node, the input current is your I injected, which is a function of time because it's a spike. And this injected current flows into two components, is further subdivided into two components. One is the current which will flow through this capacitive branch, and another is which will flow through this resistive branch. Now, since the input resistance of a comparator is generally very, very high, we are considering that no current is flowing in this direction. So if we look at the individual components of the capacitive and resistive branch and we break them down, it helps us to get how the membrane potential is changing as a function of time. So first, the capacitive branch, the current is C mem dV by dt, where V is V mem, and in the resistive branch, the current which is flowing is V mem, which is over here, minus V rest, which is over here, divided by R. And if you rearrange the terms, you are able to see this final fundamental equation, which dictates that the change in membrane potential as a function of time is a function of the integrated current, which is the second term, and also the leakage component. Here, the very important parameter is the membrane time constant, which is R mem into C mem. that is tau, and this basically governs how quickly charging and discharging or integration or leakage can happen in this particular LIF neuron. So all of this is for the condition where the membrane potential is less than the threshold voltage, because that is the integration or the leaky integration phase, which is indicated in this graph by these red lines. But what happens when the membrane potential reaches the threshold? As we know, there is a firing, and this is what happens. There is a spike that is generated at that particular instant of time, and after that the membrane potential is reset by closing this feedback loop. And these set of equations are what are implemented when you start implementing a leaky integrate fire neuron into software. Next, we look at a different model for a neuron, which is called the Hodgkin Huxley model. So far, we have looked at very simplified model, which is the leaky integrate fire model, which captures the basic integrate, threshold, and reset behavior of neurons. However, real neurons, as we had seen, are far more complex and dynamic, especially if you account for the entire range of biophysical mechanisms. And the most famous and biophysical accurate description of how neurons generate spikes come from this fascinating work by Hodgkin and Huxley in 1952. Working with giant squid axon, they performed groundbreaking work using voltage clamp experiments to measure the different ionic currents that flow through the neuron's membrane when an action potential is generated. And their work is what gives us a quantitative electrical model of the neuron, which is still the basis of modern neuroscience today. So let us have a look at the Hodgkin Huxley model, and for their groundbreaking work, they also won the Nobel Prize, I think in 1962. So in the Hodgkin Huxley model, what is common is that you have a membrane capacitance, just like you saw in your previous leaky integrate fire neuron. But in parallel with this membrane capacitance is not just one fixed resistor, but several variable conductances that represent different ion channels. These are mainly sodium, potassium, and some other leak channels, which account for other ions. Mathematically, it is described by the membrane equation. It treats the membrane like an electrical capacitor where changes in voltage dVm by dt occur because of different ionic currents. As we just described, these are your potassium, sodium, and other leak channel ionic currents, which are again counterbalanced by your injected presynaptic currents. Now, it is important to note that these separate ionic currents are driven by the difference between the membrane potential and their respective equilibrium potentials. So, as you can see, the equilibrium potential for sodium, potassium, and other leak channels are indicated by ENA, EK, EL respectively. Not only that, these ionic currents also depend on voltage gated channels, and these are represented by gating variables such as M, N, and H, which control how open or closed these channels are. An external current which is injected can also push the voltage up and down, as you can see in this particular expression. Together, these equations explain how complex interactions of ion flow can generate electrical signals inside these neurons. Although the Hodgkin Huxley model is the gold standard in explaining the generation of action potentials in actual biological neurons, as you can see, it is a very computationally heavy model because it involves 4 different differential equations which need to be solved self-consistently. And therefore, the LIF neuron, which is computationally much simpler, is what is generally used for all neural network implementations. So let's stick with the LIF neuron. It is good to know about the Hodgkin Huxley model, but for engineering purposes, the CMOS LIF neuron is more than sufficient. So as we had discussed, in CMOS, we can build these leaky integrate fire neurons using capacitor, resistor, and comparators. But this consumes a lot of area and power, making them very unsuitable for large-scale neuromorphic systems. What we ultimately want instead is a single nanoscale device, as I have pointed out over here, that behaves like a neuron on its own. It should integrate the input current, which is your I injected, and leak naturally over time as indicated over here. And when a threshold voltage is reached, it should start producing output spikes. But more importantly, the firing frequency should be directly dependent on the input current, just like in biological neurons. In biological neurons, if the injected presynaptic current is small, the spiking frequency of the neuron is low. And if it is large, there is a lot of rapid spiking. So if one physical device can reproduce this entire scale of input to output behavior, which is from integrate, fire, and encode intensity through spike rate, then we will actually truly achieve a neuromorphic neuron at the device level. So the goal is basically to replace these bulky circuits with intelligent device physics, which can mimic all these neuronal function only with one single nanoscale device. And in this case, before we start looking at these devices, an analogy will be very useful to understand. So think of the neuron as this bucket which has a hole. As water flows in and gradually fills up, that is your integration phase. But as you can see that there is a hole in this bucket, and therefore there is also leakage over time. And what essentially happens is when the bucket gets full and overflows, it's like the neuron reaching a threshold and firing a spike. After the firing is complete, as you can see, the bucket is emptied, and this is the reset process. And then you start the integration process again. So now we will begin by looking how we can build these LIF neurons using 100% CMOS process, which is very different from just CMOS compatible devices. Here we do not rely on any exotic materials. Everything is fabricated purely with standard silicon technology. And the key physical mechanism which is used to mimic neuronal effect or neuronal firing is called the single transistor latch effect. Now, the single transistor latch effect occurs only in N plus P, N plus junctions where you have a floating body or a floating base. Now, using two examples, one of a 2-terminal floating base device and another example of a 3-terminal floating body device, we will study what is this single transistor latch effect and how it helps in mimicking the behavior of neurons. So on the left hand side, the device that you see is an N plus P N plus silicon structure with a floating body or a floating base. On the top you have the N plus emitter, then you have your P base, and then you have a N plus collector. Is essentially like a BJT but a 2-terminal device, because this middle portion, which is the base, is kept floating, and you will only do 2-terminal measurements like this. And if you look at the electrical characteristics of this 2-terminal device, you notice something very interesting. Let me draw your attention to the IV characteristics shown over here. Please focus only on the blue curve. As you can see, initially at 0 bias, this device is in high resistance state. It has very low current, 1 picoampere of current. But at a particular voltage, which is called the threshold voltage, you see there is an abrupt change from high resistance state to low resistance state. And this is where this switching happens. And this abrupt switching is what mimics this neuronal firing. But if you see that after it reaches the low resistance state, it stays in the low resistance state if you keep increasing the voltage. And this is where the latching effect comes from. So it has latched on to the low resistance state. However, it is very different from a non-volatile high resistance to low resistance switching that we have seen in our eNVMs. Why is that the case? This is volatile switching. Why? Once you start pulling back the voltage in the opposite direction, you see the low resistance state equally abruptly switches back to the high resistance state at another voltage, which is called the hold voltage. So as you can see, this abrupt switching at the threshold voltage, which takes it from high resistance state to low resistance state, is what mimics the firing, whereas the automatic reset happens in the opposite direction. Now, in the 3-terminal device, we have the same structure, N plus P N plus junction, but now the floating base over here, or the floating body, is being gated by a third terminal. And this gating from a third terminal gives you a lot of tunability in fixing the threshold voltage of firing. And when we look at spiking neural networks in our final module, you will see why it is very valuable to be able to tune this excitatory behavior or firing potential of these neurons. Next, let us try to understand why do we have this single transistor latch effect in this floating body N plus P N plus junctions by examining their band diagrams. So as you can see over here, at the first stage, under a constant input current I input, the device operates below the threshold region, which is this region, and the drain voltage VDS starts to increase slowly. At this point, carriers are getting injected into the body region and they begin to accumulate. Why do they accumulate? This is because the body region, remember, is essentially floating, and this N plus P reverse bias junction is preventing any charges from escaping because of this large barrier. And this is what is the integration phase, which is very similar to the rising membrane potential in the biological neuron. So as the output voltage further increases, the critical electric field near the drain body junction becomes strong enough to trigger impact ionization. What is impact ionization? It is the new generation of electron-hole pairs which are created through the avalanche effect. And what happens is that the holes get trapped inside the floating body region, which forward biases the body source junction. And this creates a positive regenerative feedback loop because more holes increase conduction, which further increases the electric field, accelerating the impact ionization process. And once this feedback becomes self-sustaining, the device suddenly latches into a high current state or the low resistance state, and this is what is known as the firing event. And this is also exactly like the neuronal spiking. After the firing, the excess charge gradually leaks away, as you can see over here, through the PN junction, bringing the device back to its original state and ready for the next cycle of integration. So what we are seeing here is a neuron-like behavior emerging purely from semiconductor physics, integration through body charging, firing through impact ionization, and reset through leakage. And this is the essence of how the single transistor latch effect enables neuron-like behavior. Next, let's look at the actual electrical behavior of this CMOS neuron. And as you can clearly see, there are 3 distinct operating regimes depending on the input current. So in the first case, as you can see, there is a very small input current which is around 1 picoamperes. This is shown in black color in this particular graph. The device is completely inactive. Why is this the case? Because the injected charge is so small that it is completely lost through recombination and leakage. As a result, there is no triggering single transistor latch effect and the output voltage stays flat at 0 volts. This is called the sub-latch regime where no firing occurs. In the second case, with a moderate input current around 1 nanoamp, as is indicated in red color, the device enters the spiking regime. Here, the injected charge is sufficient to gradually accumulate charges in the floating body. And as a result, the voltage rises slowly, reaches the latch up or the threshold condition and fires abruptly and then resets by the mechanism we described in the previous slide. Finally, if the input current is very large, around 100 nanoamps, as shown by the blue curve, the device enters the super latch regime. In this case, the injected charge is much higher than the leakage. So the device simply remains stuck in the high voltage state around 2.25 volts. So there is no reset, there is no oscillation. It simply remains in the latched in condition, as you can see even from your IV characteristics. So the tuning of proper input current is absolutely essential to see the oscillating behavior. As you can see, below a particular threshold, there is no oscillation. Above also there is no oscillation. And in this intermediate regime, the firing frequency that you see here in kilohertz is directly proportional to the log of the input current. Similar leaky integrate fire behavior also has been shown in other works such as the 3-terminal floating body device. As you can see, there is this leaky integrate phase that you can observe when pulsed inputs are sent in the injecting terminal, and once it reaches the threshold condition of roughly 2.5 volts, there is an abrupt fire and reset. So the big advantage here is very clear that this neuron is built entirely using standard CMOS. There is no exotic materials, making it highly compatible with existing fabrication. However, because it relies on impact ionization, which generally requires large voltages, it consumes high power and also raises some reliability concern, especially over long-term cycling. So while this is CMOS friendly, it is not yet very energy efficient that you generally need in neuromorphic devices, and therefore we start looking at other candidates, especially memristors or RRAM devices to mimic neuronal behavior. Here the idea is very simple. The devices that we use exhibits volatile threshold switching, which is very, very different from non-volatile switching, which we have studied earlier for memory applications. So as you can see over here, the volatile threshold switching with its threshold voltage, where the device is going from the high resistance state abruptly jumping to low resistance state at a threshold voltage, and then on the way back giving the hysteretic effect is switching back from the low resistance state back to the high resistance state at the whole voltage, is absolutely essential to mimic neuronal behavior, because threshold switching can mimic firing, whereas the volatile returning back is going to mimic your reset functionality. And by exploiting this natural hysteresis, the transition from off to on and back, we can directly implement, integrate and fire dynamics in a single nanoscale memristive device. So in the work that I have indicated in the slides that I have referenced for you, the speciality was that this concept of using volatile threshold switching for demonstrating leaky behavior and auto reset was extended and generalized for several different physical mechanisms. So let us look at the different kind of devices and their physical mechanisms which enabled this volatile threshold switching. So the first graph that we see here consists of a niobium oxide switching element sandwiched between two tungsten electrodes. So in NbO2 based devices, this threshold switching occurs due to a field-induced phase transition. When the voltage is high enough, the material transitions from an insulating tetragonal phase to a metallic rutile phase. And this is what is responsible for the sharp switching at roughly 1 volt. So this atomic rearrangement process, which causes a sudden drop in resistance, gives us a very sharp firing event, as you can see in this image. Once this voltage is removed, it returns back to its insulating state, naturally causing a reset. In the second example, we use something called ovonic transition switching, which is a form of phase change switching which occurs in chalcogenide materials such as boron telluride, where switching is not due to atomic movement but purely because of electronic effects. Now, there are several models to explain what is the origin of this ovonic transition switching, such as thermal runaway, impact ionization, polaron collapse. And there is not a lot of consensus in the community what causes this switching, but it is very clear that it is very repeatable. It's a very fast electronically driven instability, which has some role in heating effects also, and that causes this volatile threshold switching behavior. And that is what is being employed here to create neuromorphic neurons. The third mechanism uses a modified CB-RAM structure where a conductive filament forms temporarily but dissolves immediately once the voltage drop occurs. Unlike non-volatile CB-RAMs used for memory, this volatile version provides a strong threshold switching response with very high off-state resistance, make them very suitable for neuron-like integrate and fire behavior. Next, let us try to understand how these threshold switching devices are used to implement a full-scale integrate and fire cycle. So this neuron circuit, as you can see over here, consists of just 3 elements: your threshold switching device, a capacitor which mimics the membrane capacitor, and an output resistor R out. So as you can see from the figure, during the integration phase, when the input current arrives, the membrane capacitor slowly charges, as you can see over here. Since discharge to the threshold switching device is very weak in the off state, the charge keeps accumulating and the voltage across the threshold switching device VT rises gradually. Once the VT reaches the threshold voltage, the threshold switch device abruptly switches to its on state, and this is called the firing event. At that moment, its resistance drops to the level of R out, causing a sudden voltage change across R out, which produces this output spike, as we can see in this image. Immediately after the firing, the capacitor discharges through this green path, and this is what helps in resetting the membrane potential back to its original state, and your integration cycle can again continue. So let us look at the electrical characteristics of these memristor based neurons using this image. In this panel, you can see what happens to the output voltage of these devices once you inject some current through pulses. And as you can see, as you keep increasing the magnitude of current from 25 to 30 to 42 microamps, the frequency of the firing events, as you can see from the drop in the membrane potential or the spikes that you can see in the V out, become more and more frequent. And that is what you can see in the other two implementations of threshold switching as well. So this paper essentially shows a generic framework for creating memristor neurons, and also correlates that the off-state resistance through which the discharge happens and the switching speed can be used to tune the leaky, integrate and fire behavior of these artificial neurons. Next, we move to a very interesting topic of stochastic firing of neurons. Up till now, we have focused primarily on deterministic neurons, where the firing behavior is entirely predictable. Given a certain input, the device fires at fixed threshold every time. But in biological neurons, firing is not deterministic. Real neurons are inherently stochastic. There is a lot of randomness in the spike timing and firing probability due to different biophysical mechanisms. And this stochasticity is not a disadvantage, as is in the case for von Neumann computing. It is actually a very important and powerful feature of the brain. And as we will see when we study spiking neural networks, it helps in building robust decision making under noisy environments using something called population coding. And through this seminal work from IBM research in 2016, they demonstrated that you can develop stochastic spiking neurons using PC-RAMs with GST-based material. Instead of operating the PCM in its usual non-volatile set-reset mode, they are biased near the threshold switching regime where the material exhibits volatile conduction, and under repeated voltage pulses, the device's conductance increases gradually, effectively integrating input energy over time, which is similar to the membrane potential in biological neurons and can be seen in this particular graph. However, due to the intrinsic atomic and structural fluctuations within the amorphous GST region, remember the switching characteristics of your PC-RAM devices, and these fluctuations result in cycle-to-cycle variability in the firing times of these neurons. So as you can see in the top plots, although the overall firing pattern is repetitive, the exact spike position shifts slightly across all trials, and the neuron doesn't fire exactly on the same pulse number each time. And in the bottom graph, it quantifies this variability. The interspike interval follows a Gaussian-like distribution, proving that randomness is rooted in material physics and not some external noise. Finally, we conclude with the recent demonstration of stochastic integrate fire neurons by researchers at NTHU and ITRI at Taiwan. They closely work with TSMC, which gives us an idea that these biological implementations of neurons are very interesting even to your large semiconductor manufacturing giants. Now, similar to biological neurons, the magnetic tunnel junctions which form the heart of STT MRAMs also do not switch deterministically. Under repeated injections of current, the thermal fluctuations and energy barrier variations cause probabilistic switching, meaning each firing event has built-in randomness, and this you can clearly see in this particular graph, where although the switching from parallel to anti-parallel state is happening, causing a change in output voltage, but there is no specific pattern. And this stochasticity is evident by looking at the oscilloscope traces in the top right plot, where we see random switching between resistance states over time. This is effectively spike firing. In the next plot, we see that increasing the input current leads to more frequent spiking, demonstrating that there is a clear input-output firing relationship, just like in a biological neuron. At high currents, the frequency of switching is definitely more, but the interspike gap is not always uniform. Okay, so with this, we conclude today's session where we explored how neurons can be implemented in hardware, starting from 100% CMOS compatible devices to emerging eNVMs like PC RAM and STT MRAMs, which exhibit natural stochasticity. In the next class, we will shift our focus from neurons to synapses, and we will understand how synaptic plasticity forms the core of learning and memory in all neuromorphic systems. While neurons spike, the synapses are what adapt to the environment, and this adaptation is what necessarily enables true intelligence. With this, let us conclude our today's class. Thank you very much for your attention. See you in the next class.